You might picture living on the moon as a serene sci-fi utopia. In reality, it is one of the most lethal environments humans have ever attempted to inhabit. Step into the sunshine and you are baking in 127 degrees Celsius heat. Step into a shadow and the temperature immediately plunges to -73 degrees. The extreme temperatures are only the beginning. The moon lacks a protective magnetosphere, leaving the surface exposed to relentless solar radiation. Without an atmosphere to burn up debris, the terrain is constantly pelted by micrometeorites, tiny rocks traveling at 50 meters a second, faster than a sniper bullet, capable of puncturing an oxygen tank or cracking a helmet wide open. There is no air, nothing to eat, and the environment is actively hostile to biology. This raises a difficult question. Why would humanity spend trillions of dollars to build a self-sustaining million-person metropolis in the middle of a deadly wasteland? The drive to stay comes down to one physical trait: gravity. The moon's gravitational pull is only 16% of Earth's. That simple mathematical difference changes the requirements for spaceflight. This chart shows the staggering mass of fuel required for space travel. To launch a rocket into low orbit from Earth, you need to hit roughly 35,000 kilometers per hour. To achieve that speed, 90% of the rocket's entire weight has to be fuel. But because of the low gravity on the moon, launching that same payload is 84% easier. As the diagram shifts into this node map, you can see how that efficiency transforms the moon into a central transit hub. Staging a flight to Mars or the asteroid belt is significantly more efficient if you start the journey with a full tank in lunar orbit rather than fighting Earth's gravity well. Using the moon as a staging ground makes deep space accessible, but realizing that potential requires a specific sequence of engineering victories just to keep the lights on. The first major hurdle for a permanent lunar city is power. Near the moon's equator, a single night lasts for 14 straight days. Surviving 2 weeks of freezing darkness requires more energy storage than a nascent colony can reasonably provide. Take a look at this high-contrast photograph of the lunar surface. This is Shackleton Crater, located right at the moon's south pole. NASA engineers realized that by placing their city on the ridge of this specific crater, they could bypass those deadly 14-day nights. Because of the unique tilt of the lunar south pole, the sun hangs low on the horizon almost constantly. The ridge sits in peaks of eternal light, meaning solar farms placed here can harvest sunlight 24 hours a day. That constant solar energy is fed into massive banks of graphite-based batteries to stabilize the power grid. For the gear sitting in the long, freezing shadows, engineers deployed radioactive heater units, small pellets of plutonium, to keep critical machinery from freezing solid. But the South Pole offers a second geographic perk. Deep inside craters like Shackleton, which is twice the depth of the Grand Canyon, there are pockets of permanent darkness. Those shadowed basins have preserved billions of years of volatile materials, including massive deposits of water ice. Selecting this crater provides the environmental raw materials, light and ice, necessary to begin addressing the threats of power failure and dehydration. With water and power secured, the next problem was the dirt. Lunar regolith is a fine, incredibly abrasive powder. It gets into every hinge and gasket. For early crews living in temporary metal habitats, this dust caused mechanical wear that led to air leaks and the constant threat of decompression. Shipping steel and concrete from Earth is cost-prohibitive, so engineers turned to in-situ resource utilization. By using high-intensity lasers, they melted that abrasive regolith powder into a molten state, allowing it to recrystallize into a highly durable structural ceramic. From there, autonomous 3D printers began churning out massive, interlocking architectural domes made entirely of this synthesized moon concrete. By transforming a primary hazard into a building material, engineers created thick, heavily shielded structures capable of deflecting micrometeorites and radiation. This shifted the colony from a fragile outpost to a fortified, permanent settlement. Even inside those protective domes, the human body struggles. Citizens face the psychological isolation of cabin fever alongside physiological decay caused by years of living in low gravity. To feed the population and maintain their well-being, engineers constructed vertical hydroponic farms. Cultivating leafy greens and rice under artificial light provides a local food source and a vital psychological connection to nature. To counter bone and muscle loss, they engineered massive spinning centrifuge habitats. This wireframe schematic shows how it works. By rotating a ring, the outward push of centrifugal force simulates the feeling of Earth's gravity for those inside. The math on these structures is highly unforgiving. If the centrifuge is too small, your head experiences significantly less gravity than your feet, making the simple act of turning around nauseating. To keep citizens healthy, these habitats must be at least 50 meters wide, spinning at 6 revolutions per minute, or ideally over 100 meters wide, spinning more slowly. Integrating artificial gravity with closed-loop agriculture moves the lunar presence beyond short-term research. These technologies allow humans to reside on the moon for their entire natural lifespans. A completed city like Luna Prime functions as a single, highly sensitive life support organism. The entire infrastructure is an interconnected system where AI manages the balance of oxygen, heat, and energy across millions of sensors. Because this pressurized ecosystem is so fragile, international cooperation is an absolute necessity. Armed conflict is practically impossible when a single stray bullet or exploding oxygen tank means immediate decompression for everyone. The hostility of the environment enforces peace. Compare that collaborative metropolis to this image of the Apollo missions. For decades, humanity's presence on the moon was defined by a few isolated footprints and a flag left behind in the dust. Today, people on Earth can step outside, look up at the night sky, and see the glowing lights of a bustling city reflecting back at them. By engineering survival in such a hostile vacuum, humanity has built the first definitive bridge to the rest of the solar system. We have proven that we can adapt, build, and maintain life beyond our home world.